In this lecture, I will discuss how to analyze and design beams in steel structures. So in the steel structures or in the concrete structures, basically we have to design the member against the applied loadings. And against the applied loadings, we got shear force and bending moment diagrams, and we have to check against the applied loading is it in the member capacity is present, like shear capacity is present, moment capacity is present, so that the member can fulfill or can resist the applied loading. Analysis and design of beam. A beam is a structural member in which the major deformation is bending. Shear is also present, but the more severe phenomena, that is the bending. So that's why we have to first of all go for designing against the bending moment. Then we will check for shear force, and we have to also satisfy the shear criteria. The bending moment is primarily generated due to the transverse load that is acting up downward on the beam. Beam, when a loading act on a beam, then a combination of stresses is formed that above the neutral axis compression stress will generate, and below the neutral axis tension stress will generate. And one thing more, in steel members that are strong in compression as well as in tension. So there is no issue of steel is weak in tension. Steel is strong in compression, and steel is also strong in tension. Here is an overview of the plan of a steel building. Okay, here you are seeing 4 columns. Okay, I-shaped column, and the columns which are connecting with the lines, these are beams. Okay, these are main beams that are running above the columns. So these are main beams, and the main beams are also called girders. And the beams which are connecting the main beam to the other main beam, that are secondary beams. This is secondary beam, this is secondary beam, but here is small, that is connecting main beam to this secondary beam, that is joist. That is less important beams, but with the help of that we get the favor in the designing of slabs. Then the shear, the strength, the deformation, and all things will be improved due to this beam phenomena, and we need less depth of slab due to this beam arrangement. Here is a steel bridge. Okay, here is a truss steel bridge, and here is a cross section. Before going to the cross section, first see here, you are seeing that there are longitudinal beams and here horizontal beams. Okay, and all these longitudinal beams are resting on this horizontal beam. Same, these longitudinal beam that are resting on this horizontal beam, that is horizontal beam, that is called floor beam, and these longitudinal beams that are called stringers. And after this longitudinal beam resting on the floor beam, then the ultimately floor beam are resting on this truss joints, and from the loading from these truss joints will transfer ultimately to the supports. So that is the phenomena of load transfer in the truss bridge, in case of steel bridge. And on this side there is maybe a truss, or there may be large size steel girder or steel beam. So here on the left or right side there may be truss or plate girder, that is a heavy plate girder, is a heavy beam, that is a built up section. And here you are seeing the horizontal beam, that is a floor beam, and on the floor beam there is a stringer. Okay, the stringer are resting on the floor beam, and the slab is resting on the stringers, and stringers are connecting to the slab with the shear keys and shear studs that are just like bolts are welded on the steel beams, so that the good connection develop between the concrete and steel. Deflection formula. The basic formula for the beam for the flexure stress is by denoting the elastic section modulus S and the applied bending moment by M. The bending stresses may be calculated using the Flexure formula as under. Elastic bending stress basic formula, that is basic bending stresses in beam, that is moment y over I. Y is the distance from the center, from the neutral axis to the up toe fiber, or wherever you want to find the stress. Okay, here that is a C, and in the formula that is Y. So that is the same. I is the moment of inertia. If we divide I by Y, then I over Y is the section modulus. Using the above formula, the required section modulus to resist a particular bending moment may be obtained as follows. For example, from the analysis of beam, you got the applied moment, and you also know the beam allowable stress. Then if you know the moment, the allowable stress, then you can calculate the required section modulus. You can take S on the other side and F to the bottom, M over F. Here again, S required equal to M over FA, where FA is the allowable bending stress. In a similar manner, plastic section modulus to provide a particular ultimate moment capacity may be calculated for a laterally supported and compact section by using the formula this. Here is the elastic section modulus S. Here is the plastic section modulus that we can calculate from again same formula, applied moment. Here is the yield strength. And what is the plastic section modulus? That here you can see the stress profile. Stress applied in a beam, and if that is stress is less than yield stress, this diagram will become. When the stress equal to yield, then this diagram will become. When the yielding start, then first extreme fiber start yielding, then other bottom fiber yield, then ultimately it comes to the neutral axis. Then at that point, whole section will plastify. Then at this point, this beam will or section will act as a hinge. When we got the section modulus at the elastic range, means when the elastic profile, then that is elastic section modulus. And when the section fully plastified, then at that point, when we calculate the section modulus, at that point the section modulus is plastic section modulus, mean fully plastic section. Stability of beam section. There are different types of stability. I will discuss one by one. First one is the local stability. If the width over thickness ratio, it is just like a slenderness ratio. If the width over thickness ratio, here is the width of this flange, total width of the flange divided by 2, you will get half flange width. Half flange width, that is just like a unsupported length, and you take the length from this part to this part and divide it by thickness, then you will get the slenderness ratio or the ratio value. If the width over thickness ratio of the compression flange is greater than a certain limit, flange can buckle locally. Means this member can buckle locally, not overall. Its local side can cripple, can damage by due to this criteria. The phenomena is called flange local buckling. If there is chances of buckling in the flange due to certain limit, that I will discuss in the next slides, what is the criteria. So that is flange local buckling. Similarly, if depth over thickness ratio is greater for the web, it can buckle or cripple under compression like this. Okay, I section, and the web of the I section may go buckle. So that is called web local buckling. That is web of beam. So that is web local buckling. And there is also, due to the concentrated load, there may be chance of concentration of large locally damage. So that is called web crippling due to concentrated load. So that is local stability. So we have to also perform the checks. Second one is the lateral stability. Due to lateral buckling of compression zone, the section is twisted as a whole due to the fact that the tension zone remains stable and tries to retain its position. The combined twisting, okay, so and buckling of a beam, the whole beam in a lateral direction is called lateral torsional buckling. Here, Here is a beam fixed at one side, and you can say hinge on the other on another side. Then due to the twisting of this beam, this is called lateral torsional buckling. The member can twist. Here is a channel section. When the load applied, the channel has the tendency to twist. So this similarly I section, if the side sway loading is there is an eccentricity, anything, or there is much chances that the beam buckle and twist, okay, at the same time. This is called lateral torsional buckling. It depends upon the laterally unsupported length besides the loading and dimensions and sectional dimension. Means if that is very long beam, then there is a very much chances that it goes lateral torsional buckling. Means their unsupported length matters a lot. Okay, so if there is some bracing or some arrangement that can stop the twisting, so that is a will be act as a controlling criteria for resisting lateral torsional buckling. So again, we will discuss in further in more detail in the next slides about lateral torsional buckling. Unbraced or unsupported length of beam. It is defined as the length of beam within its two sections whose compression flange is laterally supported or braced against twist of this cross section by perpendicular beams, slab, or by other means. For example, here unsupported length. Here is the support and here is support. Here is a total unsupported length. Okay, in between two supports, that is a unsupported length. And if okay, let's see another. In other words, it is the distance between 2 points braced against lateral displacement of the compression flange, denoted by LB. The section braced to prevent twist of the member are considered better for the bracing against the lateral torsional buckling. So if we provide some section here that can resist the twisting due to this lateral member from this side or at midpoint, or some bracing, then you can understand there is a less chances of buckling. So if we go for less unbraced length, that is good for us. So lateral stability against lateral torsional buckling. So first criteria, a member will be safe against lateral torsional buckling, means there is no chance of lateral torsional buckling. But there is a length criteria. If the length limit is less than from certain limit up to its full plastic capacity, means the member after yielding will go for full plastic condition, just like I have seen in the stress profiles. But the condition is that if the unbraced length of the beam is not greater than LP. If your unbraced length between supports is less than or between any bracing criteria, LB unsupported length is less than LP, then there will be no chance of lateral torsion buckling. So what is LP? That's a limiting criteria, limiting laterally unbraced length for full plastic bending capacity ZX into Fy in uniform movement case. CB is a modification factor. I will discuss again, that will be used one for no LTB, no lateral torsional buckling, and how LP will be calculated for I-shaped members, including hybrid sections, mean built up and hot roll sections, and also for channel section, LP will be calculated equal to 1.76 RY under root E over Fy. Or simply you can approximate for A36 steel, when you put Fy to 50 megapascal, E 200 gigapascal, then you will get 50 RY. Okay, radii of gyration. And if our length less than this LP, so then there will be no chance of lateral torsion buckling. Second criteria, if our length is greater than LP, now our length is LP but less than LR. A section may develop yielding. Yielding will start only at some points in case of inelastic buckling, when the unbraced length is between two limits, LP and LR. Yielding will start, but it will now go fully full plastification. Okay, so when the length is in between LP and LR. What is LR? It is again limiting laterally unbraced length for inelastic torsional buckling. Okay, if our length is less than this, then it will go for yielding at some point, but it will not go for full plastification. So what is LR? How it will calculate it? For doubly symmetric I-shaped beam, here LR. So we will use in the calculation the simple and the conservative approach, 1.95 RTS E over 0.7 FY. Then in the calculations, in the examples, we will see this formula in detail. Now I will just explaining the limits when our lengths are between this. MR means when it reaches to LR, when the length is reaches to LR, then how the moment capacity will be calculated, limiting buckling moment, dividing elastic and inelastic buckling for CB1, and CB can be defined later. I will discuss later, I already said. So equal to 0.7 FY SX divided by 10 power 6 kilonewton meter.